Hello! Today we're going to talk about Chapter 8, Linear Regression. So here is a scatter plot of the fat versus protein of Burger King menu items. So we know the correlation is 0.83, all right? So there seems to be a linear association, but the graph alone and that correlation doesn't tell you what that association is. You have to look at the model, okay? So you have to basically understand where your data is coming from, all right, to make better connections. All right, so we start with a model. The linear model is just an equation of a straight line through the data. Okay, so they're not all going to be perfect. Okay, the line's not going to go through every single point. All right, it generalizes it. Okay, it helps us understand how the values are related. As you can see in this graph, the line that's going through the points isn't going through all the points. Okay, so that's what I mean by the line won't be perfect. Your model won't be perfect. Okay, so the predicted value is being on that red line, okay, because that red line is what you would predict. The residual is you take your predicted value, your observed, so these blue dots, minus the predicted value, which is in red. Okay, predicted is a y-hat. Okay, the little thing up there. Now, make sure you understand the wording here. A negative residual means the predicted value is too big. All right, so it's an overestimate. So your predicted, the red, is bigger than the blue, what's actually observed in the real world, an overestimate. So negative is overestimate. A positive means it's an underestimate, right? That would be on top, the blue dot on top of the red line. So in this example, the estimated is 36, so that's actually on the line. The true value is 25, so that's below. So the residual is negative. Okay, so you would leave that negative on there. So some of the residuals are positive and some of them are negative, and on average they should cancel each other out. So if you add them all up, well, that doesn't really do anything. That should just get you 0. Okay, now similar to what we did with deviations, we're going to square the residuals and add the squares. Okay, so we're squaring them all basically to get rid of that negative and then add them up. So the smaller the sum, the better the fit. Okay, so the line of best fit is the line for which the sum of the squared residuals is smallest, the least squares line. Okay. Here we have the scatter plot of the z-scores of our fat and protein example. So if a burger has average protein content, it should have about average fat content too. So notice the slope moving 1 standard deviation away, and the mean, from the mean of x, is moving us r standard deviations of y, right? Rise over run. But generally moving any number of standard deviations away from the mean in x moves us r times that number of standard deviations away from the mean in y. So whatever standard deviations in x, do r times that for y. Okay? That's what you want to know. So how do we write the equation? We have y equals mx plus b. That's in algebra. In statistics, they do it this way. Don't ask me why. That's why your calculator has 2 different linear regressions, because they just couldn't agree. So in statistics, we're going to use this one. Okay? So y hat, to emphasize that the points that satisfy this equation are predicted values. Y hat is predicted. This model says that our predictions from our model follow a straight line. Okay? The model's a good one. They will scatter close around it. Now, for the slope and the y-intercept. Okay, so the slope tells us how rapidly y hat changes. All right, you write this as b1. All right, the slope is built from the correlation and the standard deviation. So r times the standard deviation of y over the standard deviation of x. Our slope is always in terms of y per unit of x. Y units per x. B0 is the y-intercept, which tells where the line crosses. Right, the y-axis, of course. All right. So we can simply just take it by using the means. The mean of y minus, well, whatever you got for B1 times x. Okay? Our intercept is always in units of y, right? You're just basically plugging in 0. Well, not plugging in 0. You're plugging in your means that should be canceling out. Now, r cannot be bigger than 1, of course, an absolute value, so it can go from -1 to 1. So each predicted y tends to be closer to its mean in standard deviations than its corresponding x was. So that's called regression to the mean, okay, because that y tends to be closer to its average, okay? All right, so let's do an example with home prices. So we have a scatter plot between house price and house size. All right, the relationship is straight with moderate scatter and no outliers. The correlation is 0.77. So you see a house that is 1 standard deviation above the mean in size. What would you expect about its price? All right, so hopefully you're thinking that it should be 0.77 standard deviations above the mean. Okay, so that's its price because you're doing r times, ooh, let me get my pen. You're doing r times the standard deviation of y over the standard deviation of x. Okay, so for 1 standard deviation for the size, then we are 0.77. All right, you didn't add for house price 2 standard deviations below the mean. What do you expect? Okay, you expect the size to be 2 times that correlation. Okay, so it's still below the mean, but it's going to be double that correlation, sorry. A friend tells you a house whose size is 1.5 standard deviations above the mean. What would you guess about its size in square feet? All right, the home is 1.5 standard deviations of the mean in size, no matter the units. Okay, so it doesn't matter if what the units are. Okay. Okay, so let's do an example. So using this these summary statistics, let's actually find the linear model. So remember your formulas. So for the first one, we would have B1 is equal to -0.641 times, let's see, the standard deviation of y divided by the standard deviation of x. And we will get approximately -0.0513. Then for B0, we will get, let's see, the mean, so 4999 minus, well, -0.641 times 61195. And we get, rounded of course, 8136.987. All right, so then our equation, so our answer would be, well, I don't know why I changed the color. So y hat equals, let's do 8136.987 plus 0.0513 x. And there's our answer. All right, so why don't you try the next one? All right, pause it. Okay, so your answer is, all right, so hopefully you got this as your answer. And as I wrote out my answer, I realized I made a mistake in the last one, so hopefully you noticed this. The negative 0.641, that's not what I did. That's not how I got that answer. What I did was I used this answer. So take this and put it here. So put B1 there. Okay, I'm not really sure why I put the correlation. I don't know. I can multitask apparently. And of course, regression and correlation are closely related, so we need to check the same conditions. Okay, so we're going to go through and check these. Quantitative variables condition, straight enough condition, outlier condition. Let's start with an example. So back to our home prices example. What does the slope of 94.454 mean? Well, an increase in home size of 1,000 square feet is associated with an increase in price of $94,454. So think about what your slope is. That is your change in y over your change in x. So our price is our y value. So that's our change in price over our change in size. And this equals 94.454. So if we leave this as a fraction, we want to make it 94.454 over 1. Well, this is money over square feet. So in thousands of square feet, so 1,000 square feet has an increase in price of $94,000.454, or $454. I can do this. All right, what are the units? Okay, well, we just did that. That is dollars per square foot. Your house is 2,000 square feet bigger than your neighbor's. How much more do you expect it to be worth? So here, it should just be double, because what you're doing is you took 2,000 square feet. Well, that's 2 times the change in its size. Well, if you do 2 times the bottom, you've got to do to the top. So 2 times the price. Okay, so 2 times 94.454. How would you interpret the y-intercept? Well, it's pretty useless, right? To get the y-intercept, to get that negative value, the size would be nothing. Okay, so the size is 0. Well, that's a negative price. So you're going to pay me for not having a property or not having any house? That doesn't seem, I don't think that's how that works. Okay, so it's not, it doesn't make sense. A negative square foot house doesn't make sense. So let's do an example. So first, you want to get out your calculator, and with this one, it is analyzing the births in women, all right, in the US. So here, let's go to our stat, edit, and input them into our list. And then we're going to make a scatter plot. So go to second y equals. Number 1, turn your scatter plot on. Make sure you're using list 1 and list 2. If it's not list 1 and list 2, press second 1 or second 2, the blue button, and then see I'm hitting the blue numbers. Alright, then I'm going to hit zoom. Oh, what did I do? Okay, I'm going to hit zoom, and I'm going to go down to number 9, I believe, zoom stat, and that's going to zoom in on my scatter plot. Okay, so I don't have to mess with the window myself. Then I want to, describe the general trend. So it seems to have a negative, moderately scattered plot. Okay, so we want to find the equation of the regression line. So go back to the main thing, hit stat, calc, and we're going to go down to lin reg a plus bx because we're statisticians, and use list 1, list 2, and I want to store the equation, so I'm going to hit alpha trace, hit y1. Then I'm going to calculate it. So there's all my values, so a, b, r, and r squared. All right. Now, if you look at y equals, notice it put that as my equation, right? It went ahead and put in my information. So now when I hit graph, you can see the line go through the points. And that is an appropriate model because it follows the general trend. It has a negative relationship. So now let's go back and look at our residuals. Remember that your residuals, with the linear model, you're assuming that the variables have a perfect relationship, okay? And they're on that perfect straight line. The residuals are part of the data that hasn't been modeled, okay? Because they're the ones that are off of that line, okay? So we have in symbols, or in words or whatever, you have your data is equal to model plus residual, or the residual is equal to data minus the model. Okay, so that's how we had it before. Now, when we plot our residuals, you want a graph of nothing. You want nothing. You want no trend. You want nothing grouped together, nothing clustered. It should just look random and useless. Okay? Absolutely boring. That's what we want. Because if it's exciting, then that means we missed something. So we want it to be boring because that tells us that we're looking at the right stuff. So let's do an example with our home prices. So you're planning to buy a home in the city with this linear model. Okay? Would you prefer to find a home with a positive or negative residual? Okay? So think about it. An overestimate or an underestimate? Negative, because that would indicate the price lower than a typical home of its size. Okay, so a negative residual is in, what's that, overestimate? Okay. All right, how much would you expect to pay for a 3,000 square foot home? Literally just plug it in. Okay, you plug it in, you should get this. So what I mean by plugging it in, just in case you're confused, we'd have the price is equal to negative 3.117, sorry, too many ones, plus 94.454 times 3, right? Because remember this was in 1,000 square feet and in $1,000. Okay. All right, and the next one, you find a nice home of that size is selling for $300,000. What's the residual? Okay, so this is what you expect. This is what you observed. Okay, so it's your expectation. All right, or I'm sorry, your observed minus your expectation. O minus E. So observed minus expectation, that's how we got 19,000. Oh, I guess I should write it out. I don't know, I'm just being lazy. 300,000 minus 280. That's a terrible 8. 250. Okay. That's your residual. I don't know, I guess I typo? I don't know, that should be 750. I'm sitting here trying to figure out where I got that from. Unless I messed up this. Oh! Wait, hold on. Let me get out the calculator. Hold on. 282. Oh, no, wait. That's not the typo. The typo is this one should have been 245. 245. My bad. So the residual standard deviation, that's of course the standard deviation of your residuals. So it measures how much the points spread around the regression line. Okay, because we always like to average everything out, right? Make sure the residual plot has about the same amount of scatter throughout, so the equal variance assumption and does the plot thicken condition. You can estimate your standard deviation of the residuals using this. Okay? We don't need to subtract the mean because the mean of the residuals is always 0. Okay? So we don't have to worry about that part in here. Okay, so we just square all the residuals, add them up, divide by n minus 2. Take the square root. Make a histogram or normal probability plot of the residuals. It should look unimodal and roughly symmetric. Apply the rule and then the normal curve, and then you can see how well your model describes the data. Okay, so you like to look at your residuals. They're helpful. All right, so let's talk about what R squared is. The variation in the residuals is the key to assessing how well the model fits. Okay, so this shows your understanding. Okay, in here you see that the total fat has a standard deviation, and then this is the standard deviation of the residuals next to it. So just the fat data by itself. If the correlation were 1 and the model predicted fat perfectly, all the residuals would be 0 and have no variation. So it would be absolutely 0. But this correlation, so this example had 0.83. So it wasn't perfect, but it was pretty good. Okay? We did see that the model residuals had less variation than total fat alone. So see how the residuals have a much smaller spread? We can determine how much of that variation is accounted for by the model and how much is left in the residuals. Okay, so what's left? That squared correlation, R squared, gives us the fraction of the data's variance. So 1 minus R squared is the one that's left over. Okay, so for our BK model, all right, you got 0.69 for R squared, so 1 minus that is 31. So 31% of the variability in total fat has been left in the residuals. Okay, so that's how much. That's why the fat varies. Okay, so in every type of analysis, you always include the statistic. Okay, it's written as R squared, and R squared of 0 means that none of the variance in the data is in the model. So all of it's still in the residuals. Okay, so this is how you would say it. So in our BK example, we had 0.69. So 69% of the variation in total fat is accounted for by variation in the protein. Okay? So the variation in fat is accounted for by the variation in the protein. Okay, hopefully this is making sense. If not, ask me in class. And back to our home prices. So we know the R squared is reported as 59.5%. So what does the R squared value mean about the relationship of price and size? Well, approximately 59.5% of the variation in price can be explained by the least squares regression line. Okay, so 59.5% of variation in price can be explained by the size. Is the correlation of price and size positive or negative? You should know it's positive since the slope is positive, right? We know that from our equation. If we measured size in square meters, would R squared change? Would the slope change? Well, R squared wouldn't change, but the slope would. R squared is about how the data is related, so that wouldn't change because the relationship wouldn't change. But the slope would, because think of that's like stretching or condensing the sides of your graph. So changing the window. Think of it like that. You own a home that is worth $100,000. Doesn't say more than the model predicts in Saratoga, California. Should you be surprised? Well, hopefully you said no, but you got to know where Saratoga is. That's in the heart of Silicon Valley, which has a high cost of living. So more than the model, that might be, especially if your model is just on, U.S. homes, or just in the state of California, it's still going to be much higher. R squared is a percentage, so you want to make sure, or it's always in between 0 and 100%. And there is no way to kind of say what makes it good. It always depends on the problem. Okay, unfortunately, that's just how it is with statistics. It just, it depends. The standard deviation of the residuals can give us more information about the usefulness of the regression. All right, so by telling how much scatter there is. Right, because if the standard deviation of the residuals is fairly large, well, then there's a lot of scatter, so it's not really hitting the line. Okay, that's not what we want. All right, you want to make sure you always report it because readers should judge for themselves. Because I said it depends on the data. Well, you might interpret it differently than someone else. So always report it. Okay, it's always about, statistics is always about variation. Okay, so it's, and R squared is a fraction of the variation of Y accounted for by the regression of X. Now, you want to make sure you satisfy all the assumptions and conditions. The quantitative variables condition, it has to be 2 quantitative variables. You can't do 2 categorical. Don't do it. I'll tell you how to do those later, but now's not the time. Straight enough condition, so obviously it assumes, the model assumes that it's linear, right? A linear model assumes linearity. I kind of like that word. So a scatter plot will let you check that the assumption is reasonable. So look at your scatter plot always. First thing, graph it. If it's not straight enough, stop. Okay, you can't use a linear model for any 2 variables, even if they are related. Okay, so make sure you're thinking about what your 2 variables are, and it has to look like a straight line. If they don't, then this whole thing is useless. All this information is useless. You have to do a scatter plot. Double check it. Some nonlinear relationships can be saved by re-expressing that. So I believe that's in chapter 9. Okay. But if that doesn't work, you got to just throw it out. And of course, you want to keep checking your linearity again after computing the regression, because you can, since you see the residuals. Okay, so check the residual plot for the standard deviation of the residuals to summarize the scatter. Okay, so look at your residual plot. Does the plot thicken condition? It should all share that same spread. Okay, it shouldn't be crazy different. Watch out for your outliers. Outliers can change everything. So, usually in statistics, people report the outliers and they either choose to keep them in our data, throw them out, or describe their data with and without the outliers. Those are your 3 options, okay? When in doubt, put them both, right? Put your information with the outlier or without. Either way, you have to explain why. So you always should look for your outliers because they can change everything. So determine if you have any, and then determine if you want to keep them or not. The data seem to clump or cluster in the scatter plot. That's a sign of for trouble, right? The scatter plots, you don't want them to, clump. You want it to be kind of follow that linear pattern. In statistics, you will see data kind of summarized like this. When that happens, you want to make sure you know what you're looking at. Okay, so usually R squared will be written out. So here you can get R by taking the square root of 0.620. Okay, that's how you get R. Remember, this is as a percentage, so you write it as a decimal. Now for your equation, we could, actually do it, or we could just look here. Under constant and coefficient, that is your y-intercept. And under the one below it, height and coefficient, that's your slope. So the equation is, let's see, we do negative 207.031 plus 5.13016x, right? Because a plus bx. Statisticians are special. Whatever, we like to be different. So yeah, make sure you know how to read that. Okay, we'll get to other stuff like degrees of freedom, standard errors, things like that later. All right. Every time you deal with data, you always want to make sure you do a reality check. Is the regression reasonable? Statistics does not come out of nowhere, okay? The results should reinforce common sense, not fly in its face. It should make sense. If the results are surprising, then you've either learned something new or you did something wrong, okay? Either you changed the way of the world is thinking or you did something wrong, okay? So make sure you know what you're doing, okay? Think about your coefficients and ask yourself whether this makes sense. And of course, always think about what can go wrong. Don't fit a straight line to a nonlinear relationship. That's just silly talk. Beware of extraordinary points. All right, so check your outliers. Either keep them or throw them out. Don't extrapolate beyond the data. The linear model may no longer hold outside of the range of data. Okay, so if you're looking at the years from 1900 to 2000, don't make predictions for year 3000. Okay, that's extrapolation. Don't infer that X causes Y because there's a good linear model. Association is not causation. Also, don't choose a model based on R squared alone, right? You can have a great R squared value, but the wrong variables. Okay, like brunettes are taller. Okay, you could have a great correlation, but that makes no sense. That's not a thing. All right, what have we learned? Okay, so this sums it up, but I feel like I summed it up, so you've got it. All right, if you got any questions, just ask me in class.